Hi and welcome to Thermodynamics for Educators Week 2 Mini Lecture 2. In this lecture I'm going to review some basic results from the first law of thermodynamics and summarise some important results that are obtained by looking at different ways that work and heat are added to or taken away from systems on a PV diagram. So let's start with the all-important first law of thermodynamics, which is summarised in an equation that looks like this. The change in internal energy, the energy inside a system, is equal to the total energy added to the system. This is, in essence, the conservation of energy. So we have a system here, its total internal energy changes by amount delta U, and that is equal to the amount of heat that is transferred to the system and the amount of work that is done on the system. Now, if we're dealing with an ideal gas, the way you do work on a system is by compressing it. And the way the system does work on its surroundings is by expanding. And as the book derives, when you're talking about compression or expansion, the work done on the system is equal to minus the pressure times the change in volume. So if the volume decreases, in other words, we've got compression, then delta V is negative and the work done is positive. So if you compress a gas, you add energy to the gas. The total energy, internal energy, goes up. Now we know from experiment the ideal gas equation, PV equals NKT. This is a macroscopic law. It's something that we figured out by looking at the behavior of gases at our level. But if we go down to the micro level and look at the atoms and molecules, we find that the total internal energy is equal to F over 2 times NKT, where F is the number of degrees of freedom, which at lower temperatures is equal to 3. And as I emphasized in the first lecture, it is very important to remember that the internal energy depends only on temperature. Temperature is a measure of internal energy and not heat. Okay, so let's take these things. The first law of thermodynamics, taking work to be done by compressing a gas. By the way, if the gas expands, then delta V is positive. That means the work done on the gas is negative. That means the gas loses energy when it expands. We have the ideal gas equation and the equation from the microphysics that relates total internal energy to NKT. So it is proportional to temperature. So we can do a variety of things to a gas. If we have it in a box with a piston, we can compress it and expand it. We can add heat through the walls, or we can insulate the walls and do things without adding heat or taking heat away from it. And we can express all these things conveniently on what is known as a PV diagram. So that is just a plot of pressure versus volume. So if you just have a box of gas sat on your table in equilibrium, it has a certain value of pressure and a certain value of volume. And so that will correspond to a single point in this PV diagram, say this point here. Now you can do a number of things to it, and we're going to go through those things one by one. We're going to start off with an isothermal process. So this is a process, this is something you do to your gas that doesn't result in any temperature change. So the change in temperature is 0. So one example would be if you started down here and moved up this red line here, that corresponds to the volume going down and the pressure going up. So you're compressing the gas. Now normally, if you press the gas quickly, the temperature goes up. That's like pumping up a bike tire. The bike pump gets hot because you are compressing the gas inside it quickly. But if you do it slowly enough, then the gas will remain in thermal equilibrium with its surroundings and the temperature will not change. So that would be an isothermal process. Now, because the temperature doesn't change, the total internal energy of the gas also doesn't change because it only depends on temperature. And the product, pressure times volume, also doesn't change because, again, that depends only on temperature. So we can rearrange this and say that pressure is equal to a constant, NKT, and is proportional to 1 divided by volume. So this red line here is a line that describes this relationship here. Pressure is proportional to 1 over volume. And if for different values of temperature, you get different lines like this. So these black lines here are all isotherms. If you move along this line, the temperature doesn't change and pressure is proportional to 1 divided by volume. Now, because the total internal energy doesn't change, we can go back to the first law and say, well, that means the total heat in this added to the system and the work done on it must add up to 0, which means that the heat flow into the system is minus the work done on the system. Now in the textbook, you'll find that combining this with the ideal gas equation here allows you to figure out an equation for the heat that enters the gas. It's NKT times the natural logarithm of the final volume divided by the initial volume. But it is important to conceptually understand this. Okay, so again, consider going up this red line. We're compressing the gas and the pressure is increasing, but the temperature is staying constant. As I said before, ordinarily, if you compress a gas quickly, it heats up. So that means if we're doing it slowly enough that the temperature stays the same, the heat that's being generated must be flowing out of the gas. That means the heat flow is negative. And that means the work done must be positive. And that makes sense because you're compressing the gas. You are pushing a piston in to your box of gas. So you are physically doing work on the gas, and therefore work is being added to the gas, work energy, and heat is being taken away from the gas. And they are exactly equal and opposite, so that there is no overall change in the internal energy. It's useful to mentally imprint these isotherms on a pressure volume diagram, even if they're not drawn there explicitly. You can easily see from this equation that at higher temperatures, they correspond to isotherms that are further to the right and higher up than the lower temperature isotherms down here. So that means when you move to the right, you're going up in temperature. When you move down, you're going down in temperature. So let's consider what happens when we move purely to the right, horizontally. This corresponds to an isobaric process, which means that the pressure is constant. If the pressure is constant, this time rearranging the ideal gas equation, we get that volume is proportional to temperature with this constant of proportionality here. And therefore the change in volume is proportional to the change in temperature. Now substitute this expression for delta V in the expression for work. So remember, work is minus P dV. Well, if you multiply this equation by minus P, you get that the work is minus NK times delta T. So the work done on the gas when you move horizontally is minus NK times the change in temperature. So for example, moving from left to right, remember the temperature goes up because you are passing through isotherms at higher and higher temperatures. So delta T is positive and then the work done is negative. And that makes sense because the volume is going up, so the gas is expanding. So the gas is doing work on its surroundings, which corresponds to negative work being done on the gas. Now we know that the total internal energy is given by this equation up here, so delta U is F over 2 NK delta T. But we also know from the first law of thermodynamics that delta U is Q plus W, which is Q plus this expression for W minus NK delta T. So moving this minus NK delta T over to the other side of the equation, we find that the heat added to the gas is equal to F plus 2 over 2 times NK delta T. So if the temperature goes up, heat is being added to the gas. So this makes sense. If we follow this path here in blue from left to right, the gas is expanding, but the pressure is constant. Think about what that means. Normally, if you take your box of gas and you expand it, you would expect the pressure to go down. In order to keep the pressure constant, you're going to have to add heat to the gas. You're going to have to heat the gas up, put energy into the gas to increase the kinetic energy of the molecules there because the volume they're in is bigger. Okay, now let's move on to paths where you go vertically up or down. These are isovolumetric processes, which is just a complicated way of saying the volume is constant. So delta V is 0, and if delta V is 0 and the work done is minus pressure times the change in volume, then that tells us that the work done on the gas must be 0. Pressure is therefore proportional to temperature in this case when volume is constant, and the change in pressure is equal to NK divided by V times the change in temperature. If the work done is 0, then we can see from the first law that delta U is just equal to Q, which we can write here, and therefore the amount of heat added to the gas is equal to the change in internal energy. So the internal energy of the gas is changing only because heat is being added or taken away. So the heat added or taken away is F over 2 NK times the change in temperature. Finally, let's consider an adiabatic process. Now, as you'll recall, an adiabatic process occurs when no heat flows into or out of the system. That means that you've taken your box of gas and you have insulated it completely. No heat can get in or out, and you do what you want to. You compress it, expand it, and so on. So if Q is 0, then from the first law of thermodynamics, the change in internal energy is equal to W, the work done. Okay. Now, the change in internal energy is given up here by F over 2 NK delta T. Here I put 3 for F, but in general this would be F. The work done is minus P times delta V, so we can substitute those two formulas in here, and we end up with this expression here. Substituting in the ideal gas equation of state, we can derive, and the book derives this, I'm not going to do it here, you can derive the following relations. You find that if you take the volume and multiply it by temperature to the power of F over 2, that's always constant no matter where you are along an adiabatic path. So you pick any 2 points and their product of V times T to the F over 2 is going to be the same. And similarly, P times V to this constant gamma, which is known as the adiabatic constant, is equal to a constant. So again, pick any 2 points along this path, take their pressures, multiply them by their volumes to the power of this number gamma, and they'll be the same. This is called the adiabatic equation of state. Now, going back to the change in internal energy being equal to the work done, you can calculate using these equations here that the work done is equal to this expression here. Now, this looks a bit of a mess, but it isn't really. It's just an expression that you have to, if you're putting numbers into it, you're going to have to be a little careful sticking it into your calculator. The adiabatic constant, or the adiabatic index as it is sometimes known, is just equal to F plus 2 divided by F. So when F is 3, when you've got 3 degrees of freedom, as you do for a gas that's made up of single atoms, then this is equal to 5/3. So a lot of this is derived in the textbook. I just wanted to summarize it and put it all in context. There are 4 different ways of affecting changes in the state of a gas. And I've summarized all these results here. So these are the 4 processes: isothermal, isobaric, isovolumetric, and adiabatic. And I've summarized what happens to the volume, temperature, pressure, and internal energy, and also how much heat and work are added to the gas in each case. And finally, each of these paths is given by an equation. Each of these lines here is given by an equation, and those equations are given down here. So for isothermal, you've got pressure is equal to a constant divided by volume. That gives you these black curves here. For isobaric processes, pressure is constant, so that gives you the horizontal lines. For isovolumetric processes, the volume is constant, that gives you the vertical lines. And for adiabatic processes, the pressure times volume to the power of gamma is equal to a constant. So pressure in this case is equal to a constant divided by V to the gamma. So contrast that with isothermal processes when pressure is equal to a constant just divided by volume. So this gives rise to these steeper curves that are called adiabats. I want to make one final point. If you want to go from state A to state B of a gas, so state A is at a lower pressure and a higher volume, state B is at a lower volume and a higher pressure. There are a number of ways you could do it. You could do it by going up along an adiabat. So in other words, you could insulate your box, you could push in your piston and compress the gas. Or you could leave it uninsulated, and you could compress it whilst keeping the pressure constant, which would mean that all the time you're compressing it, you're also allowing heat to flow out of the gas. And then you could keep the volume constant and raise the pressure by adding heat into the gas again. So there are different ways of getting from A to B. Now, it's important that each of these different paths results in a different amount of heat or work to get from A to B. That means Q and W, work and heat, are not state variables. A gas in state B does not have a certain amount of heat or work. You can do different amounts to get from A to B. A simple example of this is heating up your food. So suppose you want to heat something up to, say, 150 degrees Celsius. Then you could stick it in the oven. In that case, you are only adding heat to the food. You're not doing work on it. And that gets you up to 150 degrees Celsius. You could also put it in a microwave. A microwave doesn't add heat to food. A microwave does work on food. A microwave generates an electromagnetic field which actually does work on the food, and that causes the temperature to go up. So in a microwave, you're not adding heat to food, you're doing work on it. And you can get up to the same temperature. So you get your food out, and it's at 150 degrees Celsius. There's no way of knowing, though, whether it got there because you added heat to it, or it got there because you did work on it. So that food does not contain a certain amount of heat or work. It is characterized by a certain temperature, which means its internal energy is a state variable. It tells you what state it's in. So internal energy, pressure, volume, and temperature are state variables. They are unique to these individual points on the PV diagram. And finally, any equation involving state variables is called an equation of state, which is sometimes abbreviated to EOS. So PV equals NKT is the ideal gas equation of state. PV to the power gamma is equal to a constant is the adiabatic equation of state.